Hey kids, it's me again, Professor Nichols, with a brand new topic. Batteries, batteries, oh the infinite wonders of batteries. We see batteries, we use batteries, we love batteries. They are part of our lives, but do you know how they actually work? I do, and that's what I'm going to be explaining to you today. Now, before we get into the statistics, facts, and equations on how batteries run, let me go ahead and deliver you a short history bit on the battery. We know how they run, we know what they look like, but the sad part is, we don't know exactly who invented the first battery, but whoever this was that invented the first battery is missing out because I'm sure we would all like to give them a big round of applause and our gratitude for inventions such as these. Oh, great things. So, whoever came up with this idea, please show yourself in a history book or something by the end of eternity so someone can thank you. Thank you. Now, the first battery probably didn't look like this, or this, but, to our knowledge, it could have looked something like this. Yep, the first discovered battery, found in Baghdad, Iraq. They were preserved in these glazed ceramic or terracotta pots. The small battery was stored inside a tube inside the pots. Archaeologists discovered this baby in 1936, dating it to be over 2,000 years old. The Baghdad battery followed traits of what we call today a Voltic pile, invented and named after Alessandro Volta. Hey, anyone familiar with the word volt? Heh, a lesson for another day. Anyway, so what we have here is a standard Voltic pile consisting of copper and zinc. As you see here, one end is copper face, the other end is zinc, and separating the two are damp plates called electrolytes. The electrolyte wall acts as a conductor, as it directs the flow of electrons from the anode to the cathode. Over here, we see an old-style Voltic pile. The electrolyte is so damp that if we stood it straight up, all the water and liquids would gush out. I'm going to be making something similar to a Voltic pile property-wise. I will be using copper and zinc to compile a galvanic cell. This is what a galvanic cell does. The zinc loses electrons. The electrons flow through what we call the salt bridge until it's dissolved and positive on the copper electrode. By definition, the cathode is the electrode where gain of electron takes place. So, the copper electrode is the cathode. The cathode attracts cations, so it has a negative charge. The anode is the electrode which acts as a negative terminal, distributing the electrons. Negatively charged anions move toward the anodes. In this case, copper is the cathode and zinc is the anode. Why are galvanic cells so relevant to us in the real world? Bob Quiz! What is the use for galvanic cells? A. To be the main contributor to the successful function of lead batteries, or B. To be the main contributor to the successful function of Superman's laser vision. I'll give you a hint. It's A. Yeah, the lead-acid batteries. Not too big of a deal, right? What do? They are only the most common source of backup energy for telephone and computer centers, grid energy storage, and off-grid household electric power systems, and lighting in case of power failure. Not too big of a deal. Let's get into the materials that make this baby. We have our galvanic nails, our film covered, any special film color, our vinegar, our copper wire, our H2O or water, and our salt. Now, it doesn't have to be any special type of salt, no special type of water, no special type of copper wire, no special type of vinegar, any color film will do, but please make sure the nails are galvanic. Okay, let's get started.